Okay, so we heard about the missions of CERN, and my job is to talk more about what one might regard as being the primary mission, namely pushing forward the frontiers of knowledge. I may say a couple of words towards the end about developing new technologies, but that's going to be mainly Freddie who's going to talk about that. And you've already heard about the two other aspects of CERN's missions. So in particular, I'm going to talk about the Higgs boson and beyond. And I thought I'd provide a little bit of a historical introduction. This here is a picture of Mr. Higgs, the guy who came up with the idea of the Higgs boson. This is an idea that he proposed back in 1964. This picture was actually taken in 1965 when he was working out some details of his theory. In this business, you sometimes have to be very patient. So, Patrick has already told you that there are thousands of scientists from dozens of countries around the world who are involved in research at CERN. And sometimes people wonder, well, why? Okay. And one of the answers I think that I would give to this question is illustrated by this famous painting by Paul Gauguin. So these people are asking themselves very basic questions about our place in the universe. Where do we come from? What are we? And where are we going? And I would answer the question by saying that we particle physicists, this is our day job, to answer Gauguin's questions, of course, in a certain language of physics, but nevertheless asking very fundamental questions that I think everybody everywhere on the planet is interested in knowing the answers to. So we're going to be hearing a little bit later on about SKA. SKA, of course, is a next-generation telescope which looks at the universe on the very largest possible scale. We are interested in the very small scales, and on this logarithmic ruler, roughly halfway along the line, is the human scale. This is actually a picture of Albert Einstein and his kid sister. So we know that inside Einstein and his kid sister, there are molecules. Those molecules are made of atoms. The atoms have electrons orbiting around nuclei. And since the first half of the 20th century, we've known that those nuclei are made out of protons and neutrons. And since the second half of the 20th century, we've known that those protons and neutrons are made up out of quarks. And our job now as particle physicists is to understand systematically the properties of these particles of matter and to go on to the next step. So as I said, astronomers, they look at the universe on the very largest possible scale. But many of the very fundamental questions about the universe can only be answered by exploring what happens at the very smallest scales. And you can think of the LHC as being a sort of super microscope which is capable of studying the laws of physics that obtained in the very earliest stages of the Big Bang, and therefore perhaps answering some of the fundamental questions about the universe. So during the first half of the last century, many of these discoveries were made using cosmic rays. For example, antimatter was discovered in cosmic rays. But around the middle of the last century, physicists realized that if they wanted to continue the study in a more systematic way, they needed to do controlled experiments in the laboratory with known particles, with known energies, hitting known detectors at known times, and that is what gave rise to accelerator physics. So those studies in the second half of the 20th century gave rise to what we call the standard model of particle physics. And I'd like to underline the fact that one of the key proponents of this theory was Abdus Salam from Pakistan, who together with two American physicists, Glashow and Weinberg, proposed what we now call the standard model, making essential use of the ideas of Peter Higgs and colleagues that I mentioned earlier on. And well, the first experimental verifications of predictions of this model came in the 1970s. More detailed measurements were done in the 1980s. And so by the time of the 2000s, I think we were all pretty much convinced that the standard model had to be correct. So the standard model consists of particles of matter. So on the left here, you have the quarks. On the right, you have the electron, a couple of other heavier, rather similar particles. And we have the fundamental interactions. So going along from left to right, we have gravity, electromagnetism, which everybody is very familiar with. Then we have inside the nucleus the weak nuclear force responsible for forms of radioactivity, and the strong nuclear force responsible for holding nuclei together. So I like to think of what you see on this slide as being, in some sense, the cosmic DNA, which encodes all the information you need to make all the visible stuff in the universe. Notice I said the word visible. I'll come back to that later on. Well, almost all the information. Because one thing that is not explained on this slide is where do particle masses come from. And that is where, sorry, I shouldn't have come to that yet. Okay, so where the masses come from, this is where Mr. Higgs comes in. So the next slide is supposed to remind you that the standard model is not enough. And since we're talking about 007, I came up with 7 reasons why the standard model is not enough. So one thing is that the vacuum, the state of the universe, according to our current calculations, is unstable. I talked about the standard model explaining the visible matter in the universe, but it doesn't explain the invisible dark matter, which is, in fact, according to astronomers, most of the matter in the universe. It doesn't explain where the matter in the universe came from in the first place and why there is this difference between matter and antimatter. You've undoubtedly heard of neutrinos. They also have masses, but these are not explained by the Higgs boson or the standard model. We don't understand why the universe is so big and old. This has a potential explanation in terms of the theory of cosmological inflation that you've probably heard a lot about in the last couple of months. There's a problem with the different scales of physics. How do we make a true quantum theory of gravity? And so there's many reasons for thinking that there is physics beyond the standard model. And of course, this is going to be one of the principal objectives of future accelerator projects that we'll be discussing in a moment. So if I come back to Gauguin's questions and I translate them into the language of particle physics, what are we becomes, what is matter made of and why do things weigh? Where do we come from? What is the origin of matter? What is the dark matter that fills the universe? What is going to happen to the universe in the future? What happened to the universe in the past? Why is the universe such a big and old place? And of course, one of the other things that we speculate about in the middle of the night is whether, in addition to the parts of the universe that we can see, there may not be additional invisible extra dimensions. So our job as particle physicists is to ask these questions, which of course many of them go far beyond the standard model. But maybe our friend Mr. Higgs can help us answer at least some of them. So I want to say just a little bit more about the problem of why things weigh. So of course Newton taught us that things weigh because they have mass, and energy told us, Einstein told us that energy is related to mass. Unfortunately, these distinguished gentlemen somehow forgot to explain where the mass came from in the first place. And that is where Peter Higgs comes in. And a key aspect of his theory is that there should be a particle in addition to the previously known particles of the standard model, the Higgs boson, and that is the particle that was discovered at CERN 2 years ago. I can't resist mentioning that Peter Higgs was a student at King's College London. So I would like to give you some sort of physical picture for the Higgs idea, and I hope my friends from Africa and MENA will not mind if I propose an analogy based on snow. So imagine yourself in the middle of Siberia. So you've got this medium extending as far as the eye can see in all directions, uniform, isotropic. And this is like the Higgs field that fills all of space, homogeneous and isotropic. When you go through this medium, if you're lucky, you may have skis, and then you sort of skim across the top of the medium without sinking into it, without interacting with the snow, without interacting with that Higgs field. Maybe like a photon that travels very fast, like the skier, at the speed of light. Or you may interact with that Higgs snow field. Like somebody with snowshoes, you sink into the snow, you go slower than the skier, you travel at less than the speed of light. Maybe like an electron that has a mass. And then finally, maybe you're trying to cross Siberia just in your hiking boots. Then you're going to go very slowly because you interact very deeply with that snow field. You have a very strong interaction with the Higgs boson. So, depending on how you interact with this universal Higgs field, you acquire a larger or a smaller mass. But the key way of testing this theory was to discover the quantum of this Higgs snow field. So we know what is the quantum of snow. It's the snowflake. And the basic building block of this Higgs field is, as I mentioned, the Higgs boson. So this is, somebody else quoted The Economist earlier on in this meeting. It's an invaluable scientific resource. And here they give you a plot of how long it took between the proposal of various different particles to their discovery. And the longest delay was between the proposal of the Higgs boson and its discovery, which was 48 years. I like to encourage my friends who believe in, for example, supersymmetry as a possible extension of the standard model, that their theory has only been around so far for 43 years. So I won't say very much about the Large Hadron Collider. You'll hear more about it from Freddie. It's now completed its first run. As Freddie will tell you, it's being prepared for its second run, which will be at higher energies, with all sorts of possibilities for discovering physics beyond the Higgs boson. Just to show you a couple of events that are interpreted as the Higgs boson. So previously the Atlas detector was mentioned. This is the experiment that the young Palestinian student is now working on. And you see in this picture here computer reconstruction of the detector and the various different components. And you see 4 red lines coming out of this interaction here. And those are interpreted as probable evidence of a Higgs boson. And this is another example from the other big detector looking for new physics. In this particular case, this could be a Higgs boson decaying into a pair of photons. I might mention that many colleagues from the Middle East are collaborating on this CMS experiment. So this just shows you how the signal for the Higgs boson grew as a function of time. So on the left here, you have a known particle, the Z boson. On the right, you have another, well, actually pair production of that Z boson. And then here you can see a peak appearing in the middle, and that is the infamous Higgs boson. It looks even more convincing when you put a histogram under it. So this is the seminar where the discovery of the Higgs boson was announced. And I'd like to salute Lynn Evans here, who is the guy primarily responsible for the construction of the LHC. And this is a picture of Peter Higgs with another one of the inventors of this idea, Francois Englert. They had proposed this idea 48 years previously, but this was actually the first time that they met in the CERN auditorium the day that their particle was discovered. So, as you know, the Swedish Academy has now concluded that beyond any reasonable doubt, this particle that was discovered at CERN is indeed the Higgs boson. Quotation is actually taken from a paper that I wrote with my PhD student. Interestingly, this quotation does not appear in the published version of the paper, because the referee told us that beyond any reasonable doubt is not a scientific term. So it was good enough for the Swedish Academy, but not for the journal. So as I commented, there's plenty of reasons for thinking that there is physics beyond the standard model, and let me just mention a couple of examples. So one is the dark matter in the universe. So the standard model explains all the visible matter in the universe, but astronomers tell us that there's 5 or 10 times as much invisible dark matter. This is required in order for galaxies to form and in order to hold galaxies together. And it could very well be that this dark matter is made up of particles, possibly supersymmetric particles, that we might stand a chance of producing either in the LHC or in a next generation accelerator. I mentioned earlier on antimatter. So antimatter, of course, was discovered in cosmic rays, as I mentioned. It's also used routinely in medical diagnosis. Around the world, thousands of patients have been diagnosed using PET scanners. The P in PET stands for positron, the antiparticle of the electron. So we physicists are very puzzled by the fact that matter and antimatter are not quite equal and opposite, which was what Dirac and others thought before 1964. And we think that it's that small difference between matter and antimatter which may explain why the universe today contains matter, but not any significant amounts of antimatter. And there are experiments at the LHC and elsewhere that are trying to see whether this is indeed the right explanation. So those are just a couple of examples of the physics beyond the standard model that we're now studying. I think I'm probably out of time now, but I would like to emphasize a point that I made earlier on, that I think fundamental science of the sort that we do at CERN is the basis for innovation and hence also economic development. And I'd just like to mention James Clerk Maxwell, who unified electricity and magnetism, and he, of course, has a lot to answer for. I could also mention Albert Einstein. When he proposed the theory of relativity, it seemed like something very abstract and not at all relevant to everyday life. But now, of course, there's a multi-billion industry based on the global positioning system, and this relies on special and general relativity for the interpretation of the signals. So I think I'll finish at that point. I won't show the rest of my slides. I just wanted, as I said, to emphasize that fundamental science is the basis of innovation and economic development. Thank you.